Okay, friends, we'll start up again. All right, so I want to practice this a little bit because there are questions on the exam about E versus Z. So it's good to figure this out. So I'm going to draw an example molecule, and we'll do a few of these together. Da, da, da. Okay, so let's first worry about assigning E versus Z, and then we can name the molecule if we want to. So again, we're going to conceptually deal with each that doesn't make sense, goodness, each carbon of the double bond individually. So we'll call this one A and this one B. And our question is, which of the two groups attached to carbon A is going to be the highest priority one? So we look at the two atoms, chlorine versus carbon. If they're not the same atom, then we can choose which one wins directly. And in this case, chlorine's heavier than carbon. So chlorine is the highest priority group on carbon A. Notice what we did not do there. We did not add up the mass of all of these groups as a whole and compare it to chlorine. It was simply chlorine versus carbon. That's important. People mix that up. On carbon B, we make the comparison. Carbon versus hydrogen. Again, that's an easy comparison. Carbon is our highest priority group. Those two groups on A and B respectively are on the same side. So what is the stereochemical descriptor for this double bond? Z. Good. Okay. So now let's start trying to put it together with the name of the overall molecule. We know that there's going to be a Z in there. Looking at this molecule, we have to decide now. We need to know what our root is, we need to know what the suffix is, and we need to know what the prefix is, if any. So our highest priority functional group here is, and you'll learn this in, from the list that's in your study guide, is the ketone. All right, so this is our highest priority functional group. Highest priority functional group is the ketone. And the appropriate suffix for ketone is -one. All right? Okay. So now we need to figure out what the root is. The root has two parts. One tells you number of carbons. The other tells you whether or not there's double bonds. To figure out what the root is going to be for number of carbons, we want to choose the longest chain that contains the highest priority functional group. Okay, so that's rule one. And we're going to start counting in a way that gives that highest priority functional group the lowest number possible. So I'm going to start here, 1, 2, 3, 4, 5. Now I'm at a branch point. I could go either of two ways, but I'm going to choose to go the way that gives me the longest chain. So 5, 6, 7. So my root is going to have hept in it. It's got a double bond between carbon 3 and 4, so I need to add 3-ene. And with a ketone is a carbon-oxygen it has a carbon-oxygen double bond, and then that carbonyl group carbon is bonded to two other carbons. So if we just leave the -one there, it is not at all clear where that carbon-oxygen double bond should be. So we have to say where it is. So we got to put a number there. And we're going to put the number immediately in front of the own. It's not good enough to write 3,2-heptene own because we're not exactly sure which one is 3 and which one is 2. So in this case, we have to just stop worrying about whether it's easy to pronounce and put the numbers immediately before the functional group that they refer to. So, yes? Would it be okay to put the 2 in front of the hept? Probably, as long as you can draw it unambiguously from the structure. So you'd have to be betting there that somebody's not going to get confused. If you write it hept 3-ene 2-one, it's unpronounceable, but it's informative. All right? Yeah. The 2 tells you where the ketone is. Yeah. Because a ketone involves a carbon that's doubly bonded to oxygen, we call that a carbonyl group, where the carbonyl carbon is bonded to 2 other carbons. It's part of the chain. It's not at one end or the other. See, with the carboxylic acid, it's always at the end of the chain, so it's obvious that it's 1, and we don't have to write 1 there. But for the ketone, you do. Yeah. Okay, what else? Yeah. Right. So we need for the prefix, we've got to have, we have a methyl group on carbon 5, chloro on carbon 3. Technically, there's a rule for they're supposed to maybe go in alphabetical order, but I don't care at all. So we'll keep the rule, but if you don't worry about it. There's also some rule about when to use dashes and when not to. I don't care about that either. Yeah.
Quick question. So if we were to switch the ketone group and the 5-methyl group,
yeah.
Just for ordering purposes, would you start ordering? Would the 1 be at the 7 to maintain the lowest number for the highest?
Okay. Hold on. I got to draw what you're proposing.
Because there's the methyl group that would be switched to the number 2. So.
Yikes. Okay, so yes, you would choose, if you put the ketone somewhere else, that might alter your numbering scheme so that the highest priority functional group could still have the lowest number. Right, you choose the numbering scheme that gives the highest priority functional group the lowest possible number. Now, that's not that big of a deal because even if you number it the other way, you can still draw the structure unambiguously. So I'm not going to give you 2 options with names where the only difference is they both unambiguously describe the structure, but one of them is wrong on a technicality because of numbering of the chain. All right? Okay. Yes?
Do you always start with the prefixes with the lowest carbon number?
Do you always start with the prefixes with the lowest carbon number? I don't actually know. I think it's alphabetical order, but if it's, but it doesn't matter. I don't care about that particular rule. So in other words, if you had written on your paper, if this were a free response exam and you had written on your paper 5-methyl 3-chloro, I would instruct the TA graders to give you full credit for that answer. On a multiple choice exam, it's a little bit less confusing, but yeah. Yes?
Which functional groups would you like us to know for the test?
Which functional groups would you like to know for the test? Really, let's see. We started talking about them and then got into naming. I want you to know what they're all called. The ones up here in group 1 where you have 3 bonds to a heteroatom, you won't need to know their suffixes. I'm sorry, you won't need to know their prefixes because they're always the highest priority functional group if they're there. Ones that are in the lower groups, so group 2 is a group that has 2 bonds between carbon and a heteroatom. That includes ketones and aldehydes. You should know both their prefixes and their suffixes. The suffix for the ketone is -one. The suffix for the aldehyde is -al. The prefix for both of them is -oxo. Maybe it's -oxa. I can't remember which. I don't care. It's -oxo. Okay? Those are maybe the ones that are most important. The other functional groups you should know, but their suffixes aren't that important because they'll often be substituents, and we'll call them as prefixes. So group 3 is one bond between carbon and a heteroatom. That would include alcohols, alkyl halides. Depending on the molecule, the suffix for the alcohol is -ol. The prefix is hydroxy. Yeah.
So like maybe you'll more than likely give us a ketone or something else that's the high priority. You won't have to compare it like
So what I won't do is I'm not going to have you name a molecule that has both a ketone and an aldehyde, and you're going to have to decide which is the highest priority among those two. I'm also not going to give you an acid and an ester and have you try to figure that out. But the study guide will give you an idea of the kind of things that you ought to be able to do. Yes? How come I didn't put ether? I should. I mean, this is not a complete list. Ethers are challenging to name because the two carbons on either side are can be different. And I really am not going to give you ethers to name, especially as high priority functional groups. There is a way to do it, and if you want to know it, you can come talk to me about it, but it's not that big of a deal. Yeah.
So like the highest priority is group 1.
Right. Yeah, so you can rank functional groups in priority just based on how many bonds between carbon and a heteroatom, oxygen or nitrogen. Amines are also down in this group. The suffix for an amine is just amine. The prefix is amino. Some of those seem sort of obvious, so yeah, go ahead.
Let's do that. It didn't really explain what was going on very well when it comes to having parentheses with R and S.
Okay, right. So the R and the S stuff we will not do till chapter 5. I put it there for completeness because we will see it's an important part of the name, but not right now. R versus S has to do with something called a stereocenter. Assigning R versus S is going to be the exact same process as E versus Z, but we'll deal with that in a little bit. Okay, others, go ahead.
We talked about like 3 bonds that have 2 bonds. Can R be a heteroatom?
So sort of at the bottom is just the alkane, right? If it's just and those are very easy to name. If it's just 2 carbons and it's all hydrocarbon, that's ethane. If there's 3 carbons and it's just hydrocarbon, that's propane, except you can't spell it that way. And so on. Yeah.
So, like, the example I wrote down is like, for Esther, there's like O, and then R.
Yeah.
So in my mind, there's 2 heteroatoms with carbon bond with the R.
Okay, so generally with esters, the R here, at least in these functional groups, is going to be something carbon-based, like an alkyl group or maybe a benzene ring or something like that. There are functional groups where this is a heteroatom, but we won't worry about naming them.
You still classify that in that top group.
Yes, this has got 1, 2, 3. The carbon here, 1, 2, 3 bonds to a heteroatom. Yeah. So each bond, pi and sigma count independently. Yeah. Ester naming is a little bit tricky because you have to name this part over here and this part here. Usually this part is a small group, and so usually you name that just a methyl group, but I'm not really that worried about naming of esters. Okay. Right, so then to finish this molecule off, we would put the Z in parentheses at the front. We don't need a number on that Z because there's only one double bond in the molecule, and so it's clear from the name which double bond that one refers to. There's no other options. Maybe I'll show you an example where there are other options. Yes? Okay. All right. So the way you're going to encounter nomenclature questions is just which of the following is, I say the name, you pick the right structure. Or which of the following is the correct name for this structure. So being able to detect errors is more important than having it all memorized completely well. I don't know. All right, let's do this one. I think this one's also out of the study guide. It's delightful because there's so many double bonds. Yay. Okay, so highest priority functional group is what? Carboxylic acid, so this is going to be an oic acid. Our root is going to need to account for all of the carbons in the longest chain that contains the carboxylic acid. I'm counting 10. So that's dec or deca. Either is fine. I have how many double bonds? 4. Okay. So I'm going to need an ene in there. But there's 4 of them, so I'm going to need a tetraene. Right? And then I need to say which atoms they're on. And so I'm going to put, you could put these numbers either immediately before the tetraene or you could put them in front of the deca. So I'm going to go, let's see, 2, 4, 6, 8, tetraene oic acid. We good so far? Substituents, I've got methyls on 3, 6, and 9. So that's going to be 3, 6, 9 trimethyl. Deca 2, 4, 6, 8 tetraene oic acid. Okay, and now we need to assign E versus Z at all of those carbons. Let's do the easy ones. No? You got it? Okay, sorry. I didn't realize I was saying it. Okay, so the one between 4 and 5 is pretty simple. That's just regular cis versus trans. The carbons beat hydrogens on either side, and so that double bond is E. How about the one between 2 and 3? Take a minute and figure that out. Okay, anybody want to take a shot? Go ahead. Is it E? Okay, I think so. which group on carbon 2 is the priority one? Yep, carbonyl carbon there is our priority group. Oops, whatever. All right, and how about on the other side? Which group on carbon 3 is the high priority one? Okay, this one right here. And you could tell that how, because both of those atoms here and here are carbon. So how did you decide that 4 was the one? Okay, what's it bonded to? This carbon's bonded to one other carbon and 3 hydrogens. This one's bonded. And in this case, a pi bond counts, you count the sigma and the pi bond. Double bonds count twice. So carbon 4 would have been bonded to 1, 2, 3 carbons and 1 hydrogen in terms of the tie-breaking procedure. And so, yeah, 4 is the winner. All right, so this double bond is E. 6, the bond between 6 and 7, for similar reasons, is going to be E. How about the one between 8 and 9? Doesn't matter, because 2 methyl groups attached to carbon 9, so the name is unambiguous. So at the very front of the molecule, we put in parentheses the E's and Z's. However, this time we have to put their numbers with them so we know which ones we're talking about. 2E, 4E, 6E. Technically, those E versus Z, those are supposed to be italicized, but I can guarantee you that I will never ask you a question where the right answer has an italicized E and the wrong answer is identical except the E is not italicized, because that's dumb. Or rather, that would be too evil even for me. Okay? Let's see. Let me see if there's some other examples that would be good to do. Fine. So practice E and Z. You should get good at that. I would say if you don't practice that and you're bad at it, you're going to be disappointed, because there will be more than one question that you will get wrong. Okay, go ahead.
I have a question about decant
Mm-hmm.
tetramer. The tetraene, because for, oh yeah.
Yep.
That's for,
Yep, exactly. Good. Yeah.
Though not possible in this molecule, let's say that the double bond between 8 and 9 is gone, and so you have 2 methyl groups on that 9th carbon. But you just put 9, 9.
Oh, so you're asking what if we erase this and do, yes, you would. I think that's an interesting question. I'm not exactly sure is the answer. But yeah, I think you would call that 3,6,9,9 tetramethyl. Yeah. Okay, so this one doesn't involve E versus Z, but it involves the bane of your existence. Maybe that's only the bane of your existence because I'm telling you it is. Maybe you're fine with 6-membered rings, in which case that's great. Go ahead. That's right. The trimethyl came because we had 3 methyl group substituents. Yep. Yeah, that's where the tri came from. All right, yeah.
Back to all the E's.
Yeah.
Why did we even need to check this? Because it looks like it's a simple enough molecule where like, it was clear that it's an E.
So let me draw just one of the stereoisomers.
Yeah, the other one was oh, there's obviously a difference here.
This is the EZZ option.
Which bond are we taking?
All of, well, I'm sorry, I'm just naming them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is a stereoisomer because the connectivity is the same, but the shape is different. Do you see how the main chain zigs and zags here, whereas here it goes down and then back up?
Yeah.
Okay. That shape's different enough that you would not have known which of these to draw if you didn't have the E's and Z's.
Okay. If I was just comparing like, oh, it's a carbon and a carbon, carbon and a carbon, and a carbon. So I just got confused by comparing all these things.
Okay. Yeah, the reason for all of this is just that we can't rotate around double bonds. So whether those two high priority groups are on the same side of the double bond versus opposite sides, those two options are actually two different molecules. All right. So for rings, we name rings in a similar way, only the root of a molecule with a ring is going to have cyclo in front of it. Okay? So, and then we count the number of atoms in the ring. 1, 2, 3, 4, 5, 6. So that's cyclohexane, okay, as part of our root. If there were any double bonds, we would use ene instead. So part 1 is cyclohex. That tells you it's a 6-membered ring. That's number of carbons, and then ane is the appropriate second part of the root because there are no double bonds. Highest priority functional group here is the ketone, so again we're going to use one, and we're going to number around the ring, starting with the highest priority functional group, and we're going to do so in a way that gives you the lowest numbers to the most stuff. But again, you can draw the molecule unambiguously even if you numbered it the wrong way, and so that's not going to be a major issue. Do you see how if I number this way, I have 2 groups that are 2 and 3 and only 1 group that's 6? If I started this way, I'd have 2 groups that were 5 and 6, so it's the lowest option. Yeah?
In this case, why don't we start with the methyl group on 6?
Great question. Why don't we start the counting of the chain with the methyl group and go around and count all the way here? I don't know, other than it's easier to deal with the ring as the core structure and then name things coming off of it as a substituent. This is at the very edge of things that you would be asked to name. If it gets much more complicated than this, there is a name for it, but nobody cares what it is. Hold on. Oh, shoot. Yeah. All right. So we would say cyclohexane, or some people like to get rid of the E, cyclohexanone, because it's more pronounceable, easy for me to say. We would have a 2 ethyl group, 3 bromo, 6 methyl. We would do that in alphabetical order, but we really don't care about that. So 3 bromo, I can't alphabetize. 3 bromo, 2 ethyl, 6 methyl, cyclohexanone. Now, what I'm not showing you is, and there was a question earlier about these R and S numbers. I will tell you that at each of these carbons, there is another option. This ethyl group could be up, the bromo group could be up, and the methyl group could be down. And we have to have a way of specifying that, and we'll learn that in Chapter 5, but we're going to ignore that now. Yeah? Do I need to put a 1 for the ketone? You can if you want to, and it certainly wouldn't be wrong. But based on the rule that in a ring I start with the highest priority functional group, then it's sort of implied.
And if that was 5 carbon, what did you say?
Cyclopenta, yeah, cyclopentane, cyclobutane, cyclopropane. There's no such thing as cycloethane, as you can see. Or I suppose there would, but it's just the double bond. I don't know. Okay, yeah, sorry. Go ahead.
Should we worry about isopropyl?
Yes, good question. Should you worry about isopropyl? Let me address that in just a second. I saw another hand. Was this about? Yeah, go ahead. Oh, what would I do if I had 2 ketones? I would number them and I would call it a dione. Yeah. For example, you asked, by popular demand, 2,4-pentane dione. Yuck. Okay. No, so the question about is about, your text does go into some things about some substituents, which we have non-systematic names for. A lot of these, you got to understand, chemistry, nobody sat down and planned how it was going to go, and so, but hey, at least the nomenclature is better than if you ever learn about the vitamins and what they're called. It just makes no sense whatsoever. There's some of it's not in order of discovery, and it had something to do with fat versus not fat soluble, but even that went away. So it's better than that world. But in any case, yeah, there are still vestiges of old names that we just can't get rid of because they're so common. An example of that is this benzene ring that has an oxygen on it, which I've told you we call phenol instead of hydroxybenzene. I haven't told you how to name benzene-like molecules, and I won't in 351, so that's fine. But no, the question was about some alkyl groups that sometimes have specific names. So as an example, this group is propanol. But if we put the OH on carbon 2, we call that isopropanol. Isopropanol is rubbing alcohol, by the way. And the reason it's called isopropanol is because it's an isomer of propanol, and it's the only other isomer that's possible. But that sort of iso nomenclature persisted to the point where sometimes if we have this, and this is again our 1, 2, 3, 4, 5, 6, this is hexanoic acid, sometimes people will, suppose I had that group there, sometimes it's simpler. There is a way to name a substituent that itself is branched, and it's complicated, so we're not going to worry about it. But sometimes people will look at that and say, oh, it's a 3-carbon group, but it's attached via carbon 2, so we can call that 2-isopropyl hexanoic acid. There's another way to do it, and this one technically isn't IUPAC consistent, but people will do that. I'm not going to push you on that or quiz you on that. I might use the term isopropyl group, and so as long as you can follow along and know what I'm talking about, that's useful. It gets even worse because if you have butane with 4 carbons, then you take one of the carbons and put it here. This is called isobutane. But then if you start adding either of these as substituents, it gets kind of nasty. So imagine a chain of some molecule, and then you have 1, 2, 4 carbons, and then that's attached to the chain. This would be called a butyl group, but if it were attached, if it were the same 4-carbon chain but attached via the carbon 2, we would call that a sec-butyl group. And if we instead attached isobutane, we would call that an isobutyl group. Are you tired yet? You want to nap yet? And if we attached isobutane not on this carbon but on the one in the middle, we would call that a tert butyl group. That has to do with a way of talking about carbons. Carbons that are bonded to only one other carbon are called primary carbons. Carbons that are bonded to 2 other carbons are called secondary carbons. Carbons that are bonded to 3 other carbons are called tertiary carbons. So the sec-butyl group is a butyl group attached to the main chain through a secondary carbon. An isobutyl group is an isobutane attached to the main chain through the primary carbon. And a tert butyl group is a isobutane attached to the main chain through the tertiary carbon. I'm not going to quiz you on that. I can promise you I will never use, I will almost never that I can think of use sec-butyl. I might use isobutyl once, but I would only do that in 352, so probably you're fine there. We'll use tert butyl all the time because it shows up a lot. And butyl is not that hard. So I would say as long as you sort of know what the tert butyl, or sometimes we call it T-butyl, is versus a butyl group versus an isopropyl group, you're probably okay. None of that is going to be in nomenclature questions, though. That's just going to be in how we talk about molecules. All right. Okay, so that's worth some practice, but don't make the mistake of doing too much practice. You should be really good at assigning E versus Z. You should be able to do that in your sleep, okay? In terms of naming molecules, you're always going to be able to find a molecule you can't name. So don't try to go down the rabbit hole because you will. It'll be like this weird dream I had once. That's still one of the scariest dreams I had. I was in some place running away from somebody, and I walked into a room and there were a lot of doors, and I walked into another room and there were just a lot more doors, and then in another room, and I realized I was never getting out of that place because there was no way I was going to remember which of all these doors I had gone through. And then I wake up. So it's real fun to sleep in the same room with me. I'm a snorer, so when I was in 6th grade, we went on some field trip, and the rest of the guys had to wake me up in the night because I was snoring too loudly. What's that? It was in a cabin or something like that. Oh, I just went back to sleep and started snoring again. Showed them. I now have an apnea device because I have sleep apnea, which is actually awesome because I feel like Darth Vader when I go to sleep, so that's cool. But when I have nightmares and sometimes wake up thrashing around, it gets really fun because I'll be like this and it'll toss the sleep apnea device onto the floor and make a loud sound, and then everybody's awake, which is always kind of fun. Don't know why we're talking about that. I apologize. So, okay. Is there anything more you want to do, any more practice you want to do about nomenclature? I hate it, but I know you worry about it, so. Okay. All right. I want to just give you then a preview of, and this won't be on the exam this time, but it's an important part of organic chemistry, and it's only alluded to a little bit in Chapter 3. And we won't spend a huge amount of time on it, and there's not that many kinds of questions you can ask about it. A lot of them are just qualitative, explain why questions, but This is really important for biochemistry and biology. We call, and the subject is non-covalent interactions. You may have learned about them in other terms in general chemistry, but these are any attractive interactions between molecules that don't involve a covalent bond. So we'll call one is ionic interactions, and that is just the attraction between a positive charge and a negative charge, right? You may have learned about something called the Ionic Bond in general chemistry, and whether or not you think about that as being real depends on your frame of reference. If you like dealing with crystalline inorganic compounds, then it's okay, I guess, to think about ionic bonds. It does take a lot of temperature to melt sodium chloride, and so from that perspective, you might think an ionic bond is strong. But if it is, then why do you put sodium chloride in water and it just dissolves? So really, there isn't really an ionic bond. The ionic bond is an electrostatic attraction between 2 point charges. And it's just Coulomb's law. Like charges attract each other. And the reason salt can dissolve is because you can replace the interaction between the sodium and the chloride with a lot of weaker but more numerous interactions between water and each of the ions. So ionic interaction would be the interaction between two charges. What I'm showing you here is an example of what you may have learned, is called an ion-dipole interaction. You recognize that oxygen's more electronegative than hydrogen, and so the oxygen should be electron rich, the hydrogen should be electron poor. We can indicate that with a delta minus on the oxygen and a delta plus on the hydrogens. We can also draw an arrow with the arrow towards the negative end of the dipole. But each of these water molecules can align itself to surround this charge, and they will fully compensate for the fact that that sodium is no longer close to the chloride. Okay? This is what happens when you dissolve salt in water. You're replacing an interaction directly between the two ions with many more weaker but still more numerous interactions between dipoles and the ions. Okay? One consistent thing between ionic interactions and ion-dipole interactions, and really all of the things that we'll talk about today is, and next time, is distance dependence. So for ionic interactions, Coulomb's law has the form, I forget, it's force, or we could do energy. K, charge 1, charge 2, and R is in the denominator. And this constant includes pi and the permittivity of the vacuum stuff, but this interaction, the energy of this interaction falls off as the charges get farther away from each other. The dependence, and we won't talk about the math, but you can look it up. As we go from point charges to dipoles, the distance dependence gets stronger. We get more R's in the denominator, so the interactions fall off faster with distance. Let's see. You've also heard, I'm sure, of dipole-dipole interactions and hydrogen bonding. Have you ever wondered what the difference between dipole-dipole interactions and hydrogen bonding is? There really isn't one. Hydrogen's just a special case. And because hydrogen is small, dipoles that involve hydrogen can get closer than dipoles that do not. So we'll come back to this, but there's other interactions called interactions between either charges or dipoles with induced dipoles, and then there are interactions of induced dipoles with each other. And we'll talk about them because they're important for understanding the world around you. So with that, good luck on your exam, and I will see you Monday.